Hi, I just want to show you something cool that I found out while learning math. So here is a double pendulum and it's swinging. And you can see also in the charts next to it, the cumulative error that accumulates, also the step errors that are occurring in each step. So this is really interesting and I'd like to talk about it and hope you find it interesting. This uses differential equations and Taylor series to actually calculate this physically accurately. But the thing is that, so here is the differential equations that actually guide this. This is a second order ordinary differential equation, I believe. Um, and you can, maybe I'll put this up or you can read about it. But however, the thing is, we are using what's called a Taylor series expansion to estimate this differential equation. And Taylor series turns out to be very interesting. Normally, if you just look at this, this is a ever expanding series, and you can see the similarities. See, this is the second order, third order. So this keeps going on and on. To be able to actually know, to estimate this process perfectly, you would need a Taylor series of infinite length. But here we are actually truncating it at the third derivative, which would be the Taylor series rank 2. And when we do it this way, we can see that the error just accumulates. And this is just, I suppose, unavoidable. I actually did some research due to the. It's not only unavoidable because you would need the infinite Taylor series, but also that the way the computer stores the decimals, there's a limiting factor on how many decimals you can score. So what you're watching here as this double pendulum is actually pretty accurate depending on its initial conditions and whatnot. However, it's not very accurate. Another thing that actually determines this is the time step calculation that is used um, in the in the calculation of the differential equation. If you lower this, if the animation will slow down, but also the error should slow down. I believe. I mean, get smaller. Well, actually, rather more exciting part is that if we increase this Taylor order to 3, then that would mean that we are using a longer version of this Taylor series. See, it says local truncation error because the error at each step is the difference between the exact solution and the Euler's approximation. We are also using an Euler's formula. There are different ways to approximate this. Euler's method is based on the truncated Taylor series expansion. When we increase the Taylor series rank, that means we are considering more of the Taylor series, which reduces error. So if we run this again, now we should see smaller. See, the error accumulation has actually uh, quite was reduced, although we saw a big spike here. If we go to a higher order, that means we are using even a longer sequence of Taylor series, and as you can see, the error accumulates much slowly. We can go even as far as up to 6, I believe. And let's run this. So essentially, I mean, this is a physical system, and this is a physically accurate simulation of this pendulum using differential equations, using Euler's method and whatnot. So this may all sound, you know, pretty daunting to you, but honestly, if you just read a little bit about it, at least at the meta level, you'll find it very interesting. I mean, you don't exactly have to understand the equations. If you understand the general ideas behind it, it becomes very fascinating, like why this Taylor series is used and things like that. Like, for example, let's quickly ask. Can you please create a HTML page explaining the Taylor series and show it where it kind of comes from the Power series in nice notation and latex, so that we visually it's visually striking, and just explain how it's used. Let's just run this real quick to end it. So this is all very interesting to me, and I wanted to kind of explore this further. You can also, I found out you can actually use this funk animation from Matplotlib to animate, so that's actually pretty good. You can also see our constants like the gravity, length of the first pendulum. We can actually increase the length of the second pendulum. Let's make it 3. Let's see what that looks like real quick. You can do all kinds of cool, crazy things with it is we are still using the Taylor series expansion of 6. Let's go back to 2 and let's see if error accumulates differently. Maybe let's actually make this length 1 and the first leg of the pendulum 3. So it's actually getting out of the screen a little bit, but yeah, this is a lot of fun to be able to put something you learn into action. Let's also take a look at this Taylor series expansion explanation. What is a Taylor series? A powerful mathematical tool that allows us to approximate any smooth function using polynomials. So this is what it looks like. There's also a Maclaurin series, which where the c is actually 0. That looks more tidy, but as you can see, it just keeps going, and it has a pattern to it. So how Taylor series emerges, maybe you can read on this, and here the Taylor series formula approximating EX around X0. So you can actually approximate the exponential function with this. Um, Pretty beautiful. And it goes on to infinity. So you take its limit, actually. Um, and error analysis. So error comes from truncating the Taylor series because you can't use it for practical purposes for when it goes to infinity. So you have to kind of cut it at some point. I'll also say this: so this Taylor series, for those of you who are more interested, so imagine having a curve. So let's say I'm going to say roughly the movement of this pendulum is represented by this. So I have no idea if this is accurate. I mean, this is probably pretty silly, but the thing is that there is no way to know this behavior of this curve except by using tangent lines and derivatives. So in a way, if this is the position of the pendulum, let's say, okay, I know this is very rough and it doesn't correspond to reality, but to be able to determine the curve, the characteristics of the curve at any location, you draw a tangent to it at that point. So that would be this first derivative. If this was its location, then this tangent line slope will give its speed, velocity at that location. But the thing is, um, if you take the second derivative of this, then it will actually give its acceleration. So the first derivative gives velocity. The first derivative of position gives velocity. The second derivative of position, or the first derivative of velocity, gives acceleration. That would mean what's is the velocity accelerating at this point, going on to the next point. If you draw another tangent line going here, you see that as time goes on, even ever so slightly, the velocity's tangent line is going to actually curve downwards, meaning it's slowing down. But here, in this case, it would be speeding up, right? So we are taking these extra derivatives, and the third derivative of it would be what's called a jerk, or how fast the acceleration is accelerating. So essentially, all we're that at each time step, in infinitesimally small time steps, we are trying to estimate the behavior of this curve, and you do it at every time step here, 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 here. So it's an approximation. So you can see why when you go to infinity, you can perfectly approximate this curve because at infinity you are using infinitely small sections of time and how all of this stuff evolves like that. So you have a much better view of it. So anyway, maybe you'll find this exciting, maybe not. But I'll put this in the. If you want to read more about it, the code will be in the Patreon post. So I'll share more as I find out.